Hi guys, welcome to We Learning, and I'm Lavanya Elangovan, your science educator. I hope you all are safe at your home, right? Staying safe and listening to all these online classes, taking notes, and also revising those notes, right? Yes, good. So let me just give you a very small introduction about We Learning. And you know what We Learning is, right? We Learning is an online education platform where we give quality education for all students. So here at We Learning, we focus on helping students to stay on schedule, value time, and also excel in their academics, right? So do subscribe to our channel, and if you have already subscribed, share it with your friends, family members or relatives so that someone out there will have the access to quality education. So having said that, let's start today's session. So what are we going to discuss in today's session? Your same first chapter, matter in our surroundings, right? Yes. So in matter in our surroundings, what did we discuss in our previous session? Can you just recall and tell me? Just keep recalling. I'll give you here and there some time so that you can interact with me, right? And even here, I'll be checking through your comments, right? Yes. So matter, basically, we were discussing about solids, liquids and gases, and how how is a solid tightly packed and how loosely is the liquid packed and how freely is this gas packed. Right, so we were talking about their properties, the physical properties basically. So after that, we concentrated on this effect of change of temperature, right? And here in effect of change of temperature, we discussed how this solid is getting converted into liquid and how the same liquid is getting converted into gas, right? Yes or no? Yeah. So how is that getting converted? How is this exact phase change happening? It is all because of their kinetic energy, right? As we increase the temperature, they start losing their tight bonding, right? So they are having their interparticular force in between them, which they'll start lose. So as they are losing, the phase change happens. Yes or no? So this is what we were discussing. And if you haven't looked that particular class where we were elaborately looking at all this transformation, you can go very well back. You can very well go back, look that video on effect of change of temperature and then come back to this. Or if you feel, okay, fine, comfortable, okay, I've learned everything about this, I just wanted to learn some more, then we can proceed. Right? So in today's session, we will be discussing some around 3 problems, right? Some numericals only, very simple, very easy and very interesting numericals, because only if numericals are there, any content will actually register in your mind. Is that clear? So yes. Can you see 3 scales here? Yeah. So what is this? So just by looking this, what is coming in your mind? What is it looking like? It's looking like a thermometer, yes or no? Yes. So what exactly will a thermometer do? It will detect heat, right? And it will tell us in terms of readings. So this much amount of heat is there. For example, if we are having fever or something like that, we'll go to a doctor. Doctor will first check our temperature, right? He'll not just touch and see, okay, fine, you're hot, but he'll use an instrument just like this, which is called as a thermometer. He'll insert it in your mouth and he'll take it out and look at the reading, right? So now we'll see how those readings came. Is that clear? So basically, to measure this temperature, we've got 3 scales: Kelvin, Celsius, Fahrenheit. Is that clear? So talking about this, Kelvin, Celsius and Fahrenheit, you can actually see here. Can you see some readings here? Sorry, yeah. So here it is given, 0. Oh my God. Fine. So here it is 0. And here it is minus 273.15. And here it is minus 459.67, such a huge number. But we'll just stick with this Kelvin. What is this Kelvin? So what is this exactly Kelvin? This Celsius and Fahrenheit you would have come across in your lower classes. But Kelvin is something new, right? And here all this are lying in one particular place called as absolute zero. What is this absolute zero? From the name we can actually take, it is absolute zero, right? It is completely zero. What does that exactly mean? See here, can you see some graph like something? Here the temperature is actually reducing, right? The heat is coming down and down, and at last it's going to be complete zero where there is some amount of heat is also not there. Is it really possible on our earth? It's not possible. But this absolute zero is the lowest temperature that is theoretically possible. Okay, so theoretically possible means like we are just having it or assuming it and we are making our calculations according to it, but it is not present. Is that clear? But it is present theoretically, just for our own convenience we've made it. So that particular place you call to be an absolute zero. Is this clear? So yeah, I just wanted you to make a note of this definition because this is quite important and it's not there in your textbooks, but I just wanted you to know these things, right? So the lowest temperature that is theoretically possible at which the motion of particles which constitutes heat would be minimal. Is that clear? So that particular moment or that particular point you call that to be an absolute zero. So having absolute zero as a reference, we have this Kelvin scale. Is this clear? So what exactly is Kelvin? So Kelvin scale is something which we are having it for a SI unit. Is that clear? Yeah. So now we'll just concentrate on this. Fine. So here you can see a reading here, right? So what is this? So this particular area is where water freezes, right? So water basically freezes at 0 degrees Celsius. Is that clear? So 0 degrees Celsius is something which is given in the Celsius scale. Okay. So let it be Celsius or let it be Fahrenheit. Our measurement is with air and water. Is that clear? We will be taking only air and water as a reference. But in Kelvin scale, we will not take air and water as a reference. We will take the absolute 0 point where there is complete absence of heat. Is that clear? So what exactly is that coldness? Coldness is nothing but the complete absence of heat, just like the darkness, no? So what exactly darkness is? Darkness is a condition or darkness is a state where there is no light at all or where the presence of light is minimal. So that is darkness, no? So similar to it only, this is also, okay? Yes. So is this clear? So now I'll just show you the definition for Kelvin scale, okay? So Kelvin, this is a unit for Kelvin. You just have to write it to be capital K only. So base unit of thermodynamic temperature measurement in the International System of Units, which is the SI units. And then the Kelvin temperature scale is used by scientists because they wanted a temperature scale where 0 reflects the complete absence of thermal energy. Is this clear? Done? Yeah, so that is about the Kelvin scale where we are using it just for our reference. We are taking the reference like or from the base which is the absolute 0. And Celsius and Fahrenheit completely it will be dependent or will be taking the reference as air and water. Is that clear? So air and water. So Celsius scale we are taking it as water. And here we will be having as 0 degrees Celsius where the water exactly freezes. And the final point or the point where the water boils, you know, it is 100 degrees Celsius. Clear? Yeah, Fahrenheit. Coming to Fahrenheit. Celsius is fine, understood. Kelvin is fine, okay, fine. What is Fahrenheit? Why do we want a Fahrenheit here? When I actually gave you a situation where when you go to a doctor will measure your temperature in terms of Fahrenheit, right? So what is the exact body temperature of ours? Where will I write? I'll write it here, okay? So our body temperature is 98.6 degree Fahrenheit, right? We don't measure in Celsius. We'll preferably use only Fahrenheit. Why? Because Fahrenheit is a scale which gives a reference of very small changes also. I'll tell you how. See, can you see the difference between these two? What is the difference between these two? We'll take one reference, okay? One reference line. What is the difference? It's around 100, right? So what is the difference here? Again, 100, 0. It is 100 only. So what is the difference here? Do a quick calculation and tell me. Yes, did. 180. So that is the difference between the two points, two reference points. It is 180. So we can also say it like it is 1.8 times of the Celsius scale. So no, when you just look only this two, you will get it like this, 1.8 times. Right? Yeah. With this 1.8 times, it will measure even a very small minimum change also. And that is why we are using Fahrenheit here to measure our body temperature and even the atmospheric weather conditions, climate, everything. We are using Fahrenheit for that only. Clear? Done? Shall I move to the next slide? Yes, I hope you understand, right? Yes. Fine. As I said before, we'll do very simple problems. Okay, so with that problems, we can actually register the concepts in our mind. That is why you have problems actually, the numerical problems. So don't get panic, okay, fine. In physics, we have problems. In maths, we have problems. Even in chemistry, no. Chemistry problems are something which is really interesting. Right, yeah. Convert 300 Kelvin to Celsius scale. Very simple. So how are you going to convert? We just have to see this. Okay. So for Celsius and Kelvin, what is the relationship? Here we said like, okay, fine, it is 0 and 32, right? In that particular reference line, you just have to see. Just look at this reference line and tell me. So for Kelvin and Kelvin and Celsius, it is 273.15. But for our convenience state, we'll just take only 273. Okay, so we'll just omit that 0.5. We have to take it, but still for our convenience sake, we'll take like 273 only. So with this, how will you calculate how will you convert 300 Kelvin to Celsius? You just have to either add or subtract the 273. Yes or no? So in this case, we'll do like this. You just have to find C, right? So C equals what? Very simple. 300 Kelvin minus 273. Yes or no? So you just have to minus this. So just subtract and tell me what will you get? Very simple. Yes, come on. Do it soon. Very simple mathematics, right? It is 2 and 7. Yeah. 27. Yes or no? Fine. So 27, you just have to write it as 27 degrees Celsius. Okay. So now, when you're writing Kelvin, it will be capital K only. And when you're writing Celsius or when you're writing Fahrenheit, you just have to include this degree every time. Is that clear? So it is degree Celsius and that is your answer. Is that clear? So next, convert 80 degrees Celsius to Fahrenheit. How will you convert? Simple. This is a formula. So look at this formula. If you wanted to convert a Celsius to a Fahrenheit, very simple. It is like 9 by 5 Celsius plus 32. So what is this 9 by 5? If you divide this 9 by 5, what will you get? You will get this 1.8. So what is this 1.8? I told you in that slide, no? I'll just show you that slide. See here. So this difference is actually, I mean like from the minimum to the maximum reference. So when we take it, it is 1.8 or 180. So when we simplify it, we can assume that it is 1.8 times of the Celsius scale. Yes or no? So it is 1.8 times. So that is why we are having this 1.8 and that is this. For our calculation purpose or just to simplify it, we are having this 9 by 5. The same thing only, we are writing it as 9 by 5. Right. So what is this 32? The same. When it is 0 in Celsius scale, it is 32. It was there, right? Can you remember that? So that is this one. You just have to add it. Simple. So now when you convert, what it will happen? 9 by 5, right? So into this Celsius, what is the Celsius? 80 degrees. I'll put a bracket here so that it will be easy for you. 32. So do this quickly and tell me. Yeah. I'll just check. I'm having my phone here, so I'll just check here who is messaging me the answer first. Yes. Quick. Very simple calculation. You just have to you just have to multiply this, right? How will you do it? 5 ones are? 5 how many times are? Simple, right? I guess you know this, right? Let me check who is answering me. Shall I wait or shall I proceed? That you have to tell me. I'll just check here. Good? Good? All right. I'll do it. See, it is 16 into 9 again. So 144 plus 32. Right. So what is this 144 plus 32? 176. Right. So 176 degrees Fahrenheit. Clear? Simple, very simple. Done? Shall I proceed? Okay. So next, convert 212 degree Fahrenheit to Celsius. Simple. So here it was Celsius to Fahrenheit, you use this formula. So in this case, you can use the same formula, but with some, you just have to alter it, like here and there you have to put it. Simple. See, I'll put the same formula here, okay, because you know this formula, so I'm putting the same formula. So how will you find C? You just have to keep the C here and take the other stuff the other side. So when you take it the other side, what it will become as? So we'll just take the 32 first. So when we take the 32, it will be like F minus 32, right? F minus 32. So 32 is gone. So you have to take this 9 by 5 that side. So when you take this 9 by 5 the other side, will it be 9 by 5 there? It can be. But how? 1 by 9 by 5. We have to simplify it again. So we'll put a reciprocal 5 by 9. So what you will get? So this I'll put it into brackets into 5 by 9. So that will be your Celsius. So no? Yes. So C is F minus 32 into 5 by 9. So you just have to substitute the values here. So it is 212 F. So simple. 212 minus 32. I'll put this inside the brackets so that it will be easy for you. 5 by 9. So now tell me, just subtract and tell me, what will you get here? Simple, 2 goes and then 21 minus 3, it is 118, right? So 180 into 5 by 9. Again, 9 ones are, 9 20s are, simple, right? I'll put a 20 here. So what will you get? 20 into 5, 100. This you know. Degrees. So what do we want? We need Celsius, right? 100 degrees Celsius. That is your answer. Clear? Copy the formulas. Copy this sums also, so that when you are solving your problems, it will be easy for you. Right? So next we'll just move on to the next segment, evaporation. Right? Very interesting stuff. What exactly is evaporation? Where a liquid converts from a liquid state to a gaseous state. That is evaporation, right? So it is one of the subdivision from a vaporization, which you already know. So vaporization, we just make it into two. One is evaporation and another is a boiling. So here it is evaporation, which is a process by which water changes from a liquid to a gas or a vapor. So that is the definition for evaporation. I just wanted you to make a note of it. Make a note. Done? As I always say, you can either take a screenshot and write it down later, or pause the video, write it down. But make sure that you write it in your textbook, because written practice is a must. And you are in 9th standard, by the time you go to 10th standard, you will, as you are having a very good written practice, you will increase your speed and you will improve your handwriting also. For these two cases only, we are asking you to write it down. Clear? Yeah, I hope you would have written this. Now we'll see like what are the factors that will affect the evaporation, the rate of evaporation. So evaporation is something which happens everywhere, wherever the water is exposed, it happens, right? So for that, certain factors are there which will influence it. Whether the rate of evaporation is more, or it is increasing, or it is decreasing. Clear? First condition, increase in the surface area. So what is surface area? Very simple. I'll ask you to do an experiment, so activity, okay? Do this. Take a very small cup, pour some water and leave it out in the sunlight. And check it after 1 week. This is your first thing. And at the same time, pour the water in a plate and leave it out in the sunlight. A tumbler or a cup, and then the same amount of water in the plate, you're just leaving it in the sunlight for 1 week. This will be your homework, right? I just wanted you to find, like daily go and see like in which the evaporation has happened to more, whether in a cup or a tumbler or in a plate. You can do this activity and tell me the result, but now just guess it out. Just guess in which the rate of evaporation will be more. Obviously when the surface area is more, right? Because when the surface area is more, no, the evaporation, the contact of that particular surface to the air will be more. And as a check, can anyone hear me? Just text me, know whether you can hear me or not, because I had a glitch here. Yes? Uh, I think I'm visible and I'm thinking like I'm audible also, right? Yes, tell me something so that I'll just check with my phone here. All right, because I had a lag here, a small technical glitch, which happens. Yeah? So once you give me the confirmation, I'll start. Clear? Shall I start? I'm just waiting for your response. Okay. So can I start? Okay, fine. I guess like now it is all clear, right? So if somewhere sometimes like if some technical issues happening, please let me know. Only then I'll stop speaking, I'll go fix it, I'll ask my friends to go fix it and I'll start it again, fine? Right, clear? So I'll just start with this factors affecting evaporation, right? Okay, yeah. So the first condition, so what we were actually discussing about? We were discussing about increase in the surface area, right? And I also gave you a homework. So increase in the surface area means what? You're just increasing the area there of the surface there. So for that only I gave you two conditions where you just have to use it in a cup or a tumbler, pour water, keep it in the sunlight, and in the other case you just have to pour it in the plate, a very flat plate, keep it in the sunlight again. Right, so what will happen? You just have to look at the rate of evaporation there after a week. If it is a very hot sunny day, you can get the results in 3 days itself. But since it is so winter, I mean like winter has started or rainy season has started in my place, we'll wait for 1 week, no problem. So when we are looking at those two conditions, what you can infer? You can infer that if the surface area is increased, or when with a flat surface, the evaporation happens too much, or the rate of evaporation will be more, right? So the rate of evaporation increases. Second case, increase in temperature. You know very well, if the temperature is increasing, kinetic energy increases, which agitates the bond between the particles, and if the agitation is too much, it will result in that particular vibration, it will result in heat, and the particles will start getting converted from a liquid state to a gaseous state, which means a phase change happens, right? Or so here, so increase in temperature, obviously the rate of evaporation also increases. Third, increase in humidity. So what happens? The same case you can take when your mother is washing clothes. She is drying it in the hot sun. She can take back the clothes within 3 to 4 hours because it will be so sunny and the evaporation will be more. All the clothes would have become dry by that time. Can she expect the same thing during winter? Seriously not. She cannot expect because of the humidity in the air. So if humidity is present, the rate of evaporation decreases. Last condition, increase in the wind speed. If there is a lot of increase in the wind speed, obviously the particles will be evaporating, liquid will slowly change into gas, and if wind is washing it out, what will happen? It will carry away too much of particles with it, right? So if wind speed increases, rate of evaporation obviously increases. Okay, fine. So these are the 4 conditions which affects the rate of evaporation. I just wanted you to take a note of it. Clear? I hope you would have done it. Let me just change. Yeah. First question here, how evaporation causes cooling? So this is one of a very, very important question in your book or in your syllabus. How does evaporation causes cooling? See, when you're running too heavily in the sun, you will sweat. And after you sweat, you will feel some sort of chillness all around you. How? How is the evaporation causing cooling there? So I've given an answer here. The process of evaporation uses the energy of the liquid particles. So it is taking the energy of the liquid particles, and with that energy, it will convert from a liquid state to a gaseous state just by consuming the energy. Is that clear? So therefore, the particles absorb the energy from the surroundings in order to compensate the energy that is being lost here. Is this clear? After this particular process, it will actually result in the cooling of the surrounding area. So the first case is like the process of evaporation uses the energy of the liquid particles first. So as it is consuming the energy only, the phase transformation happens or the phase change happens from a liquid to a gas. So after that, what will happen? The particles absorb the energy from the surrounding in order to compensate the energy lost. Right. So that is exactly evaporation, and that will result in cooling actually. Is that clear? Fine. Now, evaporation is done, and you know, like evaporation is a surface phenomena which happens only in the surface of the liquid. Right. So this is the second division under vaporization, which is boiling. So what is boiling? Boiling is a bulk phenomena. Why it is a bulk phenomena? Because the entire liquid boils. Right, here you can see here, entire liquid is boiling. How? See, in evaporation, heat is from above, but in boiling, it is from below. Of course, we use any source of heat, any form of heat to boil the particular liquid. Boiling water, boiling milk, boiling tea, anything. Boiling is a bulk phenomena where the heat source is from the bottom. Is that clear? And here, we'll just take this particular vessel itself. As we are lighting the stove, this layer of liquid boils first, or it gets heated. How it is getting heated? Excuse me. Very simple process, conduction. Right, so conduction is where heat gets transferred from one place to another place through a solid. So this vessel, obviously it is a solid. So heat particles slowly move into the solid. It will transfer or conduct in the solid. So that is called as a conduction, right? So yeah. So from the solid, it moves to this liquid, this area. So in liquid, the same heat flow We just have to say it to be convection. Yes or no? So convection happens. So this layer gets heated too much, it will get heated. And you know very well, hot liquid or hot air always rises up. This is mandatory because those particles there, no, it will become very, very loose. I mean, like the particles will lose their interparticular force. They'll become less dense, light in weight. That is why they rise up. Let it be hot air, hot liquid, whatever, something which is hot, it will rise up. The same phenomena. So this layer of liquid will tend to move up. Okay, so as it is moving up, it will come to the surface here. So when this liquid, I'll make this, mark this liquid to be 1. So this 1 is moving up and it is in this place, the same 1. Is that clear? So this layer, I'll make this layer here. This layer, I'll mark this to be 2. So this 2 will come down. So that 2 will get the same heat. It will go up. It will form a layer here. The same 2. So this is 1, that is 2. Again, the next layer comes down. It will take the heat, go up. Again, this will happen to the entire liquid here. So it will come down, take the heat, go up, come down, take the heat, go up. This happens when all the liquid particles present in that container gets the equal amount of heat, then it starts boiling. Is that clear? So it is not like as soon as you keep the vessel, pour water and keep the vessel on the stove, it boils. No, it's taking time, right? So in that particular time, this is what is exactly happening. Layer by layer, it will come down, take the heat, and then it will go up. When all the particles here gets the equal amount of heat, and then it will start boiling. And after boiling, when it is completely boiling, the phase change happens. From a liquid state, the vapors will rise up. From a liquid state, it will slowly become a gas state. Is boiling clear? So boiling is a bulk phenomena where the heat source is from the bottom, from the sides also, but basically it is from the bottom. Right, so this is the definition for boiling. Make a note of it. The process in which a substance changes from a liquid state to a gaseous state. Very simple, boiling. So is this clear? Is evaporation clear and boiling clear? And you know the difference between these two also, right? And just make a note of those, I hope like you would have made a note of those factors affecting evaporation, rate of evaporation. Right? Clear? And just recall those numerical problems that we had and the formulas that we really used. Okay. So in our next session, by this session we are completing this first chapter. Next session, we'll concentrate on the important questions from this chapter and we'll be discussing those answers also. After that, we'll move to the second chapter, such an interesting chapter again. Fine? So I'll just meet you in my next session. Until then, this is Lavanya Elangovan signing off from